This conference will now be recorded.
Good morning and welcome to our Alaska Collaborative on Health and the Environment teleconference on Fukushima, A View from the Ocean with Ken Buesseler, Senior Scientist at Woods Hole Oceanographic Institution in Massachusetts. My name is Diana DeFazio, and on behalf of Alaska Community Action on Toxics, I'll be facilitating today's call. CHE Alaska is a regional partnership group of the National Collaborative on Health and the Environment. CHE Alaska aims to advance knowledge and effective action to address growing concerns about the links between human health and environmental factors. You can find more information online at akaction.org and at healthandenvironment.org. Our call will last 1 hour, and we will have time at the end for your questions. Everyone who signed up for the call should have received a link to a PDF of Ken Buesseler's presentation. If you haven't done so already, please take a moment to download it so you can follow along. The presentation can also be accessed by going to our homepage at akaction.org and clicking on the title of today's call. Now it is my pleasure to welcome and introduce Dr. Ken Buesseler, a senior scientist in marine chemistry and geochemistry at Woods Hole Oceanographic Institution in Woods Hole, Massachusetts, and director of the institution's Center for Marine and Environmental Radioactivity. Ken specializes in the study of natural and man-made radioactive isotopes in the ocean and has been collecting and analyzing seawater from around the Fukushima Daiichi plant since the radioactive leaks began over 3 years ago. In January of this year, he launched a crowdsourcing campaign and citizen science website to collect and analyze seawater along the west coast of North America as the radioactive plume travels 5,000 miles across the Pacific. Dr. Buesseler earned his PhD in marine chemistry from the Massachusetts Institute of Technology and Woods Hole Oceanographic Institution Joint Program in Oceanography. Welcome, Ken. Would you like to go ahead and begin?
Yes, my pleasure. Okay, as we heard, I'm going to try and go through in about 40 minutes here kind of what we've learned looking back from the ocean at Fukushima, what was going on in Japan, and what continues to happen to our oceans from that site. I thought I'd first reiterate a bit my background. I work at the Woods Hole Oceanographic Institution. We're about an hour and a half south of Boston on Cape Cod. We're essentially an independent, not-for-profit research organization, which means we have about 150 scientists like myself that seek mostly government funding, but also private sources to study ocean chemistry, biology, geology, physics, and engineering. We are affiliated with MIT, and my degree is with MIT, and I'll talk about that in a second. Today, I want to walk you through 3 stories pretty quickly here. One is what happened 3 years ago. So the first couple of panels on the upper part of the first slide show the reactors on the left and an image from Yokohama in the Tokyo area in June of 2011. That was my first research cruise to the site after the March 11th disasters. The lower part of that will get into then the crowdfunding that you've heard about, what we're looking at now 3 years later along the west coast of North America, and then something about this Center for Marine Radioactivity. So with that, I'll go to the second image, the second slide you have, and just reiterate that I've been doing this for quite a long time. I happen to be a younger student during the era of Chernobyl. So in 1986, I was getting my PhD that was looking at the earlier sources of fallout to the ocean, namely the atmospheric nuclear weapons testing that peaked in the 1960s. So there I was looking at things like plutonium isotopes left over in the 80s from the earlier releases when Chernobyl went off. And the right-hand panel is just one example of many of where I went to apply myself as a marine radiochemist to study the consequences and fate of those isotopes in the Black Sea to the south of Chernobyl. And we'll talk a little bit about the differences later, but remember that was pretty much a land-based event, hundreds of miles from any ocean. In the south, you have countries, Turkey, former Soviet Union bordering the Black Sea where I was working, and to the north, Scandinavia and the Baltic and North Seas. So that's my background. So we want to look at really what happened. It's called a triple disaster. We're going to go to slide 3 now, March 11, 2011. And when we had a magnitude 9 earthquake offshore, that's the first of the 3 disasters, the tsunami, and it's not really that impressive. This is a security camera looking out to the ocean. There's 4 images on slide number 3. And one shows the wave as it's approaching. The wall is about 25, the barrier in the harbor is about 25 feet tall, and so that wave that doesn't look so impressive in the top left overflows, inundates this whole area, including in the lower left where all those tanks are. The significance of that is on the same level as those tanks that are mostly covered, and in the lower right hand, the buildings are the generators for the backup power. Stepping back a bit, think about earthquakes. The shock waves themselves cause an automatic shutdown of the reactors. So we've stopped producing new electricity, but we still have all of this heat. We have a reactor core, 4 of these reactors, in fact, next to each other, 3 of them which were in operation, and you have to do something to keep them cool. And without the electrical power that was shut down regionally due to the earthquake, your backup generators, you only have a few hours of battery backup before things start to really heat up. So we have an overheating situation, and that's what caused the release of gases such as hydrogen and the explosions that I'm sure you all remember. On slide number 4, you can see the shells of the buildings, 3 of which are basically destroyed by the explosions. If you remember in the news, the puffs of smoke. So these are gases at the high temperatures that are coming out and causing an explosion in that area, something like 2 or 3 days after the earthquake on March 11th is when we started to see the explosions and atmospheric release. So that's just to remind you of what was going on land. Slide number 5 is just to remind all of us that at that time and to this day, the biggest loss of life were the 18,000 missing and dead from the tsunami damage. When I show this slide number 5 of the Sendai coastline, there's a before and after, and what you can't see, unfortunately, is the before picture. There were homes right up to the coastline there. When I was there in 2011, there was just an unbelievable scene of like the largest tornado damage you might imagine, but spreading for miles and miles. So, at the time when this was going on, they were also dealing with the destruction and still are rebuilding after the tsunami itself and the direct damage to the buildings and loss of life that accompanied that. So we shouldn't forget that when we think of Fukushima. It was just one of 3 events at the time. The next thing I want to tell you before we get into the results is a bit about how much radioactivity is in the ocean before this accident and what the sources are, because this isn't the only source of radioactivity. So slide number 6 is trying to make the point with numbers in units of becquerels of how much radioactivity is in the ocean already, and this means before Fukushima. And the lower, the largest circles are the isotopes of potassium-40 and uranium-238. And the units I will try and use throughout today are this unit of a becquerel. I just mentioned the word. It's a decay event per second. So whether I'm measuring plutonium or cesium or strontium or any isotope, we often use that same radioactivity unit. And when you add up all of the radioactivity from a given isotope in the ocean, if you look at on the right side, potassium-40, you get 15 million of these units of a petabecquerel. Now the P in front of the BQ is a 1 with 15 zeros behind it. It's a very, very large number. So the point of this slide and looking at natural isotopes is to make the point that my difficulty often as a scientist in measuring something like cesium or Fukushima, any isotope, is I have also naturally occurring isotopes to consider and make sure I can separate the decay events from those signals from Fukushima or other sources. Very briefly, the other sources, the 3 main ones, in the upper part there are the weapons testing in the atmosphere that I talked about for my thesis. About 1,000 of those petabecquerels, 950 is what it says on the left. Chernobyl is about 110 times smaller. In Fukushima, I'll talk about the different sources, but it's on the same order. By general estimates, it's a little bit lower, maybe 30 of those units, but there's really a big margin of uncertainty of how much, in this case, cesium-137, a very specific isotope, but a very abundant in all three of these cases, was released. And so what I like to tell people that for the oceans, this was unprecedented. More of the radioactivity got in the ocean from Fukushima than Chernobyl, but both of them are far smaller than what was going on in the 60s. So we need to know that, because if you look at slide 7, there's already cesium-137 in the ocean. There's already cesium-137 in lakes and drinking waters. And so the question really is, how much higher did it get after Fukushima? But you really need to know what was there beforehand. And so now, instead of adding up how much is in the ocean when you take the whole ocean, the last slide, this is how much is there per cubic meter. That's a volume, about 1,000 liters. What would be in gallons? It's about the size of a pallet on each side, 3 feet by 3 feet by 3 feet. It's a becquerel in a big volume of water. And you'll see numbers in the North Pacific of about 1 or 2. And I'll point in the red arrows to places where it's higher than average, just to remind us that we do have higher cesium in the ocean, still in the Black Sea. The number there is 16. It might be pretty small, depends on your screen. The Baltic, it's 40. And the Irish Sea between England and Ireland is about 60. So again, we're not thinking today that those are dangerous levels, but that's what we have before Fukushima. And I think it's important to know those numbers, so when we look at the arrival of new isotope off our coastline, say, is it higher or lower than what was there in other places? The slide 8, very quickly, I talked about number 1, which is the source of radionuclides from Fukushima. That's what's shown in this cartoon from the explosions. It's called atmospheric deposition. 80% of what happened, which came up in those explosions, was blown off into the ocean. That's good news for Japan. That's not good news for the ocean, but it's good news for the human population of, say, of Tokyo and those areas. It blew offshore. The number 2 is what I call direct discharge. If you remember, they had to cool those reactors, so they brought in the firefighting units, they brought in helicopters dropping water and hoses, and that caused the runoff, the direct discharge of water, and that also is important and the equal source to the atmospheric. 3 or 4, just if you're keeping track and you're hearing news, there is a continued source both from rivers and number 4 from the groundwater. And we'll talk a little bit about that, but mostly it's those first 2 sources that are the biggest concern, and that's what we'll be seeing 3 years later along our coastline. So I hope you're following along. I think one of the few plots that has an X and a Y scale is on slides 9 and 10. And I want to show this because it's important, getting back to that map, to think about the relative amount of these different isotopes and when is it considered a health concern. And so it's a timeline along the bottom, starting in 2011 for the next year. And each red dot is a measurement of cesium-137, those same becquerel per cubic meter units that were on the map. And they're right at the nuclear power plant. This is basically going into the ocean, collecting a sample, and putting a dot on this chart that registers how much is there. And you'll see the lower left, the number arrow points to 1.5. That's about what was there before. And as soon as you start seeing the red dots, they start at 10,000. They actually peak at 50 million becquerels per cubic meter. This is when, as a radiochemist, as a marine scientist, I was very concerned. It was a couple of weeks delay between some of the water that was used to cool the reactors reached the ocean. That's why it wasn't the highest right at the beginning of all of those red dots. But those are very much of health concern. If you have 50 million becquerels per cubic meter of cesium-137, you could have direct effects on, say, marine fish in those waters, mortality, reproductive effects. And the blue line that follows that down pretty quickly is response to the heroic efforts to close some of the leaks, to stop some of the drainage directly into the ocean. But as you see, the red dots don't go back near the bottom. They stay elevated. And from the start, we were telling the Japanese scientists themselves were saying there still are leaks because we did not return down to the bottom of that graph to 1 or 2, but we still have 1,000, 10,000 becquerels per cubic meter of cesium. The significance of that is really shown on slide 10, where I try to put in words what it means to me, those different levels. Again, I'm sure, I don't know if anyone here on the phone has really thought about what a becquerel is, but in rough numbers, if you're in the millions and tens of millions, you really are concerned with direct effects on organisms that live in those waters. Fortunately, it went down, but when it stays at levels of 1,000 to 10,000, we're not as concerned about the direct exposure, but when you internalize cesium, say consuming seafood, you might be concerned about eating fish that are swimming in those waters and taking up cesium. And then when you get below there, there's 7,400, by the way, is the U.S. EPA's drinking water limit. So 1 or 2 is a very small number. A few hundred is not a big number. You saw it's already 60 in the tens of thousands, and it remains over 1,000 today near Japan. We are concerned about seafood consumption. Okay, now we're going to say, where did it go? And then we'll get into the fish. So I'm an oceanographer. We try to predict based upon ocean currents. Slide 11 is a Japanese prediction of where that contamination would move in the ocean. And you see this snaky kind of pattern, I describe it as. Japan on the left, the really high numbers in red and yellow. And as you move offshore, that's almost 1,000 miles where you still see the purple off to the right here. And the snaky pattern is simply the shape and the direction of the currents. This one's called the Kuroshio. And I'm on the Atlantic coast. We have the Gulf Stream. This is a similar, very strong, very fast current. And cesium itself, it's not a particle. It's a salt. It's dissolved in the ocean. It's like putting sugar in water. So where the water moves, the cesium will move. And that's what the models are telling us, is we're expecting it to follow the currents quickly offshore and further into the Pacific. And we'll think about what that means for Alaska shortly. I'll go quickly over slide 12. I want to leave lots of time for questions, but that's just an example of data we collected in June of 2011 that was trying to, each of those dots on this little cartoon is showing you where we took our ship and tried to collect samples to analyze for cesium, tritium, strontium, a whole number of radionuclides. This particular one, if you've heard this before or not, is 134 cesium. So each of these radioactive compounds can have different isotopes, different numbers of neutrons and protons. In this case, it's the numbers of neutrons anyway. An isotope like cesium, if it's been here for a long time, has to have a very long half-life. Cesium-137, what I've talked about up till now, still with us 60 years after the atmospheric testing. 134 is a 2-year half-life. It decays very rapidly. So that means it's not going to be here 10, 20 years from now. And so we use these different isotopes to fingerprint whether the cesium I measured and the cesium I'm going to be measuring off Alaska is coming from a more recent source. So cesium-134 can only be coming from Fukushima, or was it already there? And that's the significance of the two isotopes. But we're going to kind of move on and talk about fish and then what's arriving, because I think that's probably more on people's minds here in this group. But that's kind of a scenario of what we're doing as oceanographers to study the release and the fate of the isotopes off Japan. So slide 13 is my happy Japanese fish. I say that because this was used by the Ministry of Fisheries in Japan, slide 13, to really give people a feeling of what the fate of cesium in marine life is. And that basically means the radioactive isotopes can come in with the water they're drinking or what they're eating. But just like electrolytes, potassium, any salt, it's going to go in and out of the fish very rapidly. And so unlike mercury, unlike some of the PCBs, some of the toxic organic compounds that really build up in a food chain. Salt doesn't collect in a specific organ but flushes through quite quickly. One way to think of this, how fast, I should have put a number on there, but it's if you took a fish that was contaminated with cesium-137, look at slide 13, and there's some of the isotope in the fish, some in the water, and you put that fish in a can. You took that fish and said, I'm going to collect it today, can it up. It will take 30 years, that number, for the decay of half of the cesium because of its radioactive half-life. It's already contaminated. You've taken it out of the ocean, and it's going to take a long time to see less cesium-137. A live fish, on the other hand, put in a clean environment, will lose half of the cesium in 50 days. It's an isotope that flushes through them. That's the same reason you and I might drink Gatorade or something else to replace our electrolytes. This is not the most a high bioaccumulation factor or enrichment in fish because of its chemistry and its uptake. And each isotope will be different, and in Q&A we might get to others. I'll mention strontium-90 right now, which gets caught up in bones and might stay around for 500 days, not 50 days. But that's important because when you look at slide 14 and you start to measure how much cesium is in fish, we did not see that the numbers went down. This is 2 years of data that I pulled from that same fisheries agency, and I pulled data just for bottom-dwelling fish near Fukushima, as were the ones that were the highest, and we made the point that the numbers aren't going down quickly, so you have to be adding more cesium over time. This gets back to what's going on today. We have a source that continues. The fish, it's decreasing. It's hard to see with all those little tiny dots. The scale, if you can't read it, goes from 1 to 10,000, and in the middle is the number 100 because that's the allowable limit in seafood in Japan, and numbers above that middle line are used to keep those fisheries closed. And to this day, in fact, Japan, the fisheries right off Fukushima are closed for commercial fishing. So stepping back a second, when people ask me, hey, Ken, do you eat the fish in Japan? I say, yes. These fish in this area are not sold on the market. They're not sold to foreign consumers. They've closed down these fisheries. They're losing over $1 billion a year because of this. So this is the type of data, all of those red dots, that a fisheries managing group would use to say whether it's safe or not to open fisheries. And slide 15 is just an expansion of the same type of data, showing you in different colors connected to the map on the left that it depends where you are today in Japan, what the levels in fish are. The highest closest to the source, lower to the north and south, and some of those fisheries are open right now. So I'm kind of reaching the just over halfway point. I want to get on to what's happening along our coastline. We have told you, I hope, that there was a very high amount of cesium released in 2011. It's moving with ocean currents, so slide 16 is a picture of the Pacific Ocean. It's 5,000 miles from Japan, roughly, to the west coast in the North America. And the arrows in blue are what the general direction of these currents are. That squiggly line is now a big blue arrow, the Kuroshio. So that's what's going to move the contamination to our coastline. Slide 17 is kind of a prelude, though. Before the cesium shows up by the current, you can actually swim faster if you're a bluefin tuna, one of the rare animals that can actually migrate 5,000 miles in under a couple of months, 1 to 4 are the estimates. And so we did detect, scientists in the U.S., in San Diego, in the bluefin tuna that were feeding off Japan earlier in that year, detectable levels, about 10 of those units, these becquerels per cubic meter, in the tuna off San Diego in the fall of 2011. That was the first arrival along the west coast of any Fukushima radionuclide after the air transport, after some of the explosions and the atmospheric transport. But for the oceans, they're the first arrival. The levels were low. By the way, 10 is not considered a high risk. It is still an additional risk if you were to eat every day 5 times that amount, 5 times this 10 becquerels. For an entire year, the authors of this paper suggested a number of something like 2 additional cancers in 10 million people. The concern, again, of internal consumption is cancer risk. You can never say the risk is 0. I want to make sure that's clear here, but it's a very small number. In this case, it was lower than naturally occurring isotopes that are in those same fish. The risk in the case of bluefin tuna, health-wise, would be much higher for things like mercury than this measurement of San Diego. But that's what I'm sure the Alaskans are thinking about, is what's going to be in my fisheries. And you'll always find, to this day, the 137 isotope in every fish. We don't think about it, but it's in that water, it's in fish. And the question is, how much higher will it get with the arrival of the 134 and other isotopes? I'll mention, too, because I'm sure you've seen it up there in Alaska, but the debris came next on slide 18. Debris is not radioactive. It is of concern for invasive species. I've not heard of any huge environmental catastrophes yet because of that, but it's not. We should not be concerned about radioactivity from the debris. I only show it here because it comes faster, not because it's blown by winds in addition to being moved by currents. So I'm going to go on now to probably what you signed in for, but I thought the background was really important, is, okay, how much of the cesium gets carried with those currents, the Kuroshio and the arrows that were on the last slide. So 19 is a summary of one estimate. This was a paper that came out last year, and it shows the arrival on our shorelines sometime around 2014. It might not be that visible. The islands of Hawaii are a little box south of the major part of, I'm going to call it a plume, this color, the yellows and reds that are kind of propagating through. And really the important thing on this to realize is that, one, this is just a model. This is not a measurement. It'd be great if we had data that could be on this scale to make these types of maps. We don't. So we go with our best knowledge of ocean currents. Unfortunately, that best knowledge gave us predictions, the words below, of anywhere from an extra 1 or 2 of these becquerels per cubic meter to 30. And the timeline there for different locations varies, but it's going to be showing up, I tell people, sometime this year, but at different levels and with a leg. So actually, if you look at the right-hand plot with the yellow, red, and the blue, that's showing me that in a couple of years, it's actually going to be higher than it's going to be right on the front edge. Kind of makes sense. But what's really disturbing and what concerned me when I saw this paper is there were no data to test this. And so that's really, given this type of map, given what are really often kind of incomprehensible units, becquerels, what does it mean? People were starting to ask us late last year, well, what's the level at my beach? How high is it off Alaska? What are we going to know? And that's where we first have been trying to find U.S. federal agencies to help support measurements that go along with this type of model. Those programs just don't exist. Don't get me wrong. We've tried. We've made the case several times to our NOAA, the National Oceanographic and Atmospheric Administration, about monitoring radionuclides. They do a lot of work in oceans and fisheries, but not on radionuclides. That often falls to our Department of Energy in the U.S., but they don't study the oceans. They look at those isotopes on land. And we've been able to make the case, certainly, that it's in the national interest to be doing this, but we are at a position where we had to rely, in slide 20, on our own efforts at crowdfunding to make something happen. Let's get a few measurements. I just was asked the same question enough times that we decided in January 5 months ago that we should try and organize this campaign, ourradioactiveocean.org, to see if people would be able to both then propose sites where they're most interested in, raise the fund. It's about $600 up in Alaska to get a kit to you, fill that up with water, get it back to us. So people are both raising funds with their friends, their group, and we are then trying to get as quick as we can a container. It's 5 gallons of water. It's a pretty big container. You'll see some pictures. Get the results up on the website. We have 30 sites that are now supported. And as important is to teach people about what do these numbers really mean. And so I hope you've all been to that website, ourradioactiveocean.org. On slide 21, just a summary of what we've found. That's brand new to me. I'm someone who goes to agencies and writes proposals and seeks funding. We didn't really have time for that, so we decided on our own to set this up. And the public has certainly responded with a lot of visits to our website, over 100,000 views. That's now out of date. The number of donors is up to 350, and something like $55,000 have been raised. This is a tough way to do research science, but it's been a great way, I think, to let people become involved, pick their sites, and put the information. You can decide what you think is of concern or not, and we can get some numbers. So let's look at the numbers. Slide 22 is simply where we have data online. This is already a couple weeks out of date in orange, where we have people who are either collecting funds to reach their goal with their friends, with their group. And slide 23 is just a single slide. I only need one to show you those results from San Diego up to Alaska. Again, look at those locations, maybe in Alaska. But at each location, we really haven't seen a difference so far. What we've seen is one isotope of cesium, 137. That was already there. That was on the map I showed you at the start. About 1.5 of these becquerels per cubic meter. And I use the word no Fukushima cesium yet, because this unique fingerprint, 134, isn't there. We have, by any standards, the most sensitive techniques to measure radionuclides in the ocean. Several state health departments, I know at least in Oregon, monitor for this. They can't measure anything less than about 1,000 in those units, because they're trying to protect the public from a level that's unsafe for drinking, 7,000. You don't need to measure this low of a level, but we do, because we're scientists who are concerned about the lowest possible amounts and when they're going to arrive. And so a lot of the information I was seeing on the websites, attributing some of the effects on, say, starfish die-offs to Fukushima, just really aren't borne out. If it's not in the water, we don't expect, there's no way to have a health effect if it's not here yet, but we do think it will show up sometime this year and continue to increase. And so a big effort for now is to kind of get more dots spread along the coastline and to get places where people might go back to maybe 2 or 3 times a year for the next several years. Pretty quickly, I'll just show some, you can go through them later, but I list all of the supporters, the groups that have come together to help fund us in slides 24. The next 5 slides, I show some pictures. We've been just very pleased by the way the public is moving this forward, whether it's people bringing their kids out on slide 24, surfing groups getting together and having an event. This is, new for me, and I think it's showing me that great interest people have in monitoring their environment. Whether there we have people who are very much anti-nuclear, very concerned about their exposures, and we have people who are more concerned about, showing the world how low the numbers are. It's kind of both sides, I guess. I tell people whether you're pro or anti-nuclear, we all want to know what the numbers are in the ocean, and we've found a great response. Slide 26 is San Luis Obispo. Slide 27 is up in your neck of the woods. You can tell by the clothes and the weather, but up in Alaska we have several sites now, and 28 was a junior high school group in Santa Barbara, where it's become now part of the science classes to go out and collect samples. I'm really going to go fast. I don't think we have to spend too much time on 29 and 30, but I do want to summarize by saying I certainly think the public is concerned. I don't want to make light of those concerns that this cartoon does, but I think there has been very little government response, at least on the federal level, so we've tried to meet that with this crowdfunding. We're also trying to help with education. There's so few people trained these days. That's what slide 30 is about, that we formed a center, a place in Woods Hole, where we can try and get our graduate students funded to do this type of work. I don't have to tell you that support is needed for our radioactive ocean. That's slide 32. I'll point out on slide 33, I'm getting pretty close to the end, that it's more than just measuring along the beaches. If I was to come up with a science plan, I might use things like, it's called the wave glider, that yellow surfboard on slide 33, to go out and collect samples for us. That's simply an engineering challenge. It's a $300,000 question to buy one of these, but we can have ways to be monitoring our oceans for environmental radionuclides. We just haven't applied ourselves or gotten the support to do that. The lower ankle band is we're trying to come up with ways to make it easier. Why collect these big containers? Why not take some of the same chemicals I use to isolate cesium from that big sample I'm asking you to collect for me, and put that on your ankle? And that's what the idea of the rad band is. Surfers up and down the coastline, I could see on our coastline in Japan and elsewhere, having monitoring devices that don't give you a direct readout. This isn't something you can see with a Geiger counter over seawater, but it could at least sample for us to get back to the lab, and your iPhone or your app for picking your surfing site might also have information on cesium and other elements in your environment. So there really isn't much more to say. We are trying to put information online about understanding our oceans, and that's why on slide 34 I just want to point out at the very bottom of that website there's links to a magazine called Oceanus, English and Japanese. Some of what I've said is in there. On the right, an FAQ page that if you have a question that you really want, send it to us and we'll try and put an answer up on that. And with that, I'll just thank you. And not sure how this worked. I'm not used to talking just to a phone, but thank you for your attention, and we'll try and get on to some of the other speakers and questions.
Thank you, Ken. We're just going to hear from a couple of folks in Alaska organizations, and then we'll move on to our discussion portion. So it's perfect. We have plenty of time for discussion, which is great. We appreciate that. Before we move on to your questions, I'd like to welcome Bob Shavelson, Executive Director of Cook Inlet Keeper, to talk briefly about his organization's participation in the Our Radioactive Ocean Citizen Monitoring Project.
Thanks, Danny. I really appreciate the opportunity, and really great to hear from you, Ken. I don't know if you remember, Ken, you picked up the phone in 2011 and spoke to me when I made a call back there, because like many other people, we had a lot of questions, and you're obviously the expert on this. I really appreciated your availability when I know you were very, very, very busy. For those who don't know our organization, we're a 501c3 nonprofit. We're based in Homer. We have an office in Anchorage, too. We were started in 1995, largely with the help of Pam Miller with the Alaska Community Action on Toxics. And we just celebrated our 20th anniversary of the meetings that brought us into existence, so that was nice. But we focus on water quality and salmon habitat protection, and so it was kind of natural that we were getting a lot of questions about radiation in Fukushima, and so it was a great opportunity that Ken and his partners put together here for the crowdsourcing. So we're in the process right now. I think we've got $200 towards our $600 we need for the first sample. So please go to our website or our Facebook page if anybody wants to contribute to that. And I'll just say one of the interesting things that we've been hearing is there's a lot of concern up here in Alaska about this, but there's also kind of a paradox. There's kind of a don't ask, don't tell, because obviously fish is so important, not only to our culture and our lifestyle, but commercially. And there's kind of this undercurrent of fear that if we find something that, oh my God, it might affect the marketability of our fish. So that's a sensitive issue that we've had to deal with, and having the information from Ken is super helpful, and we're hoping that the data we collect will also reinforce the fact that our fish are not being unduly impacted. So thanks for the opportunity to speak.
Thank you, Bob. Great. Thanks. Finally, I'd like to invite Alaska Community Action on Toxics Executive Director Pam Miller to talk about Alaskan concerns and ACAT's interest in setting up monitoring on St. Lawrence Island.
Thank you, Diana. Thank you, Bob, and thank you, Ken. I just want to say that we organized this call because of great concern of Alaskans about the health of our oceans, our coasts, and the safety of Alaska fish and other traditional foods. I think the question remains within the Alaska public whether state and federal agencies are doing enough. And I'm really glad that Ken is setting up the Citizen Science Monitoring Network because I think we're getting a lot of assurances. However, I think from a public perspective, there are a lot more questions at this point than answers. And there's certainly a mix of state and federal agencies that are doing various things. And there's a site on the Alaska Department of Environmental Conservation's website that provides assurances that due to the enormous volumes of water, that this water is diluted and it does not pose a health risk to Alaskans, and that our fish and shellfish from Alaskan waters are safe. So I think there are a number of us around Alaska that are interested in Ken's Citizen Science Monitoring Network, and we're certainly interested in trying to set up a site on St. Lawrence Island in the northern Bering Sea. So it's really great to hear about this and to know more about it. And I'll just start things off maybe with a question for Ken. Are there places in Alaska and along the West Coast that you think might be important to monitor but that don't yet have coverage? And then I was also interested to know how far out the fishery is closed off the coast of Japan. So start off there. Thank you so much.
Sure, my pleasure. Well, slides 22 and 23 and our website have kind of the map of where we already have sampling locations. And you really just have to look at where we don't have dots is where we need samples. And as you might imagine, there's a lot of your coastline. You know, we have Vancouver pretty well covered and something off Haida Gwaii, but not much in between there, and you get up towards Prince William Sound and Anchorage. So there are stretches, and if you look at the models, it would predict more likely the arrival sooner kind of to the north along the Alaskan coastline. The evidence so far, there was a scientist in Canada from Canadian Fisheries who did see detectable cesium-134, this fingerprint for Fukushima, offshore. This was several hundred miles offshore, not yet at the beach samples we've looked at. So that's the level he saw was about 1 or less of these becquerels per cubic meter, not in what I call these danger zones. But I do want to get back to a loaded word. You said safe. You know, each increment will change our risks. But my personal opinion is that these waters, and I will say safe personally, people can decide on their own. But when you have these tiny levels of cesium that are lower than what is there already, or there in other places where we have people in Europe swimming, others doing fisheries. If it's not in the water, I'm not concerned about the fisheries. That type of comment often comes up. So we're not measuring fish directly, but if we're not seeing it in the water, there's no way you're going to see high accumulation in fish in, say, Alaska. It will be detectable at some point, and that's where it's good to start having these discussions. What does 1 or 10 extra becquerels mean for our risk? But we shouldn't be, I'm concerned about health and safety off Japan where the levels are higher. I think you asked how far offshore they're closed. I don't know the exact number on that. The map I showed is they're bringing in fish to those ports, and it's a coastal fishery. It's something that does not reflect hundreds of miles off the Japan coast. It's a coastal fisheries, the red dots on the slide I showed from Japan.
Thank you, Ken, and thank you, Pam, for your questions. At this time, let's go ahead and open the lines for your questions for participants to ask questions of Ken or of Bob or Pam. If you'd like to ask a question, please press *2 to unmute your line. Please also state your name and affiliation, and we ask that you try to be brief just so that we can really maximize the 15 minutes that we have and get several questions in before the end of the hour. If you're not speaking, we also ask that you press *2 to mute your line again so that the sound quality remains good. Thank you.
Could I ask a question? This is Diane from Nuclear Information and Resource Service.
Yes, go ahead, Diane.
Actually, I've got two, and they're quick. One is whether doing the cesium testing is, I mean, it's exciting that it's being done at all, but I'm wondering if there are other radionuclides that might not travel with the cesium, or maybe they're just not as significant, or there aren't as many, but couldn't there be other radionuclides even if the cesium didn't measure or didn't show up? And then the other one has to do with, at, say, Diablo Canyon at San Luis Obispo, did you notice any, because there are routine releases from nuclear power reactors, and there's 2 reactors there, so did you maybe notice a little more of the cesium-134, possibly from the routine releases of the Diablo reactors?
Yeah, we're not monitoring Diablo directly, but we do have a site nearby, and we have not seen any change, and we see no detectable 134 there either. So it could be we're too far away, the releases are small. But I really want to get to your first question because that's quite important. So there are other isotopes that were released. Early on, we were most concerned about iodine-131, 8-day half-life that accumulates very high degree in things like seaweeds, 10,000 times higher in seaweed than in the ocean. Fortunately, because of the 8-day half-life, it's basically gone after a couple of months, and there aren't new releases of these shorter-lived isotopes. Why the emphasis on cesium? When the accident first happened, other isotopes are concerned with much lower concentrations when you do the dose effects or the seafood consumption for seafood. Strontium-90, I think I mentioned once already, was about 50 times lower. So what's arriving today would have 50 times less strontium-90 than cesium. We are hanging on to samples to do that analysis, but it's much more difficult to do and was less concerned. Having said that, what's happening today off Japan, levels are thousands of times lower. Those red dots go down. It's lower offshore, maybe 100 becquerels per cubic meter of cesium, but the level of strontium-90 is almost the same, and that's because of the nature of the cleanup process. The groundwaters that are a continued source tend to be enriched in strontium-90, and the tanks that leaked, 10,000 tanks in somewhat unstable conditions because of the earthquakes that happened there. 2 of them have leaked already, and it's relatively easy. The company involved has TEPCO cleaned up the water before it goes in the tanks for cesium, but not for any number of other isotopes, including strontium-90. A bit of a long-winded answer, but pointing to Japan today, I would say that the concern needs to move more towards strontium-90, and it is there at almost equal concentrations. It's a bone-seeking isotope, and therefore, I think I did mention it stays in the fish for hundreds of days, not a couple of months, and in our system as well. So we haven't seen evidence yet that it's reached levels in the ocean off Japan that we have to close fisheries for, but that is by far, to my mind, a much greater concern for new releases that'll show up on our shore 3 years from now than cesium, which is already quite low relative to the initial accident.
I have a question.
Can you let us know who you are?
Hello?
Yes.
I have a question about ocean dumping. I have 2 questions, really. Government's policies about ocean dumping of nuclear waste, I believe, around islands in the Pacific, South Pacific, and Britain was dumping high-level canisters of nuclear waste right off their shores some time back. And then looking at your chart of your graph for the Irish Sea and the Baltic Sea, do you have anything to say about why those levels are high in those places, and what about fishing there?
Great. Specifically, the Baltic Sea and Black Sea are higher in cesium because of leftover from Chernobyl. That accident, 85% of the fallout went on land, but some fell in the ocean, and that's why those basins are higher than they were and higher than other places. The Irish Sea source is nuclear fuel reprocessing at Sellafield. So things you mentioned also, canisters. There have been studies around the Farallon Islands in the U.S., canister dumping in the U.K. It's hard to detect as much release as from these other sources, the nuclear fuel reprocessing. They've shut down. I was surprised to see it still as high as it is, even though they've closed off the source at Sellafield almost completely, and that's probably due to residual cesium on the seafloor that's getting back out into the system. Now, is that high or not? It's certainly a very low number, 60 relative to, say, what the drinking water standard is, 7,400, and the fish there are considered by all standards well below either the Japanese limits, which are the strictest in the world, 100 of these becquerels, or the U.S. and Canadian limits closer to 1,000. So risks are never zero, but they're quite low. And when the tuna off San Diego were measured at 10 of these becquerels, that's when I think I mentioned the risk was an additional 1 to 2 cancers in 10 million population. So the authors didn't say it was zero, but they were more concerned about other health effects and other isotopes in those fish. So I assume, and I know the fisheries are still open in those areas that you mentioned.
So as of right now, except for those places right around Japan that are closed, are there fisheries from any other part of the world that you would say stay away from right now?
I have not seen any fisheries that are above what they are in Japan. In Japan, most of them areas are open except near Fukushima. And so that has to do with this 100 becquerel or 1,000 becquerel per kilogram limit. The fish everywhere else are below that by far, by factors of 10 to 100 or more. I did hear a report on someone who had analyzed in Alaska for fish, and it was, again, I think they didn't even detect the 134. Something that's difficult in interpreting this, and even for me, is that different labs have different detection limits, and often they're set by those health and safety standards. So if you're trying to find out if a fish is below 1,000, you use techniques that can see 500 or higher. We're a research scientist, so we try and detect levels that are well below health standards, say by a health department or an FDA. So if there were cesium, and like I said, there is cesium already in every fish because of the weapons testing in the 60s, we can detect it even when it's not considered of direct threat to human consumers.
Thank you. I would like to move on to, I think we probably have time for 1 or 2 more questions, and I'd like to
Diana?
a special invitation to our Alaska participants to ask a question.
Diana, this is
Yes.
Vi. Can I
Hi,
ask?
Vi.
Hi. I'm a native village of Savunga tribal member. Pam mentioned how our tribes on St. Lawrence Island are especially concerned about the radiation from Fukushima. I see on the map that you have data available from Norton Sound. I'm curious to see what that is. And my other question is, our main foods on St. Lawrence Island are bowhead whale, walrus, and seals. And I saw that the range for bowhead whale, Japan is included in that. And our people are very concerned about the marine mammals that we live off of. 70 to 80% of our homes eat only traditional foods. And we do have commercial fishing on St. Lawrence Island, halibut, that Norton Sound Economic Development Co-op purchases from our fishermen. So I'm curious to see if you have any of that data also.
What I can say is you can go on this website and view the results by location. And the numbers for all of those sites are less than 2 of these becquerels per cubic meter for the 137 cesium, no change, and none of the Fukushima isotope. So what that really means is those ocean currents would carry any isotope with them. Someone talked about this earlier, I think, or asked me the question. And so when I don't see 134 cesium, it's kind of like the canary in the coal mine. I don't expect to see any of the other isotopes there. So that's relatively good news. On the other hand, I share your concern about some of these fish, mammals. I'm not sampling or analyzing those. States and federal agencies are doing this in a very, I'd say, limited way is a good way of putting it. And I think people have concerns, and I keep telling when I go to Washington or try and talk to the agencies that even if we think the numbers are low or safe, or however you want to put it, people have concerns. We should be making these measurements. We owe it to everyone to have a baseline of data so you can see the changes. If something is happening, can we attribute it to one source of contaminant or another? And without measurement, we'll never know. And so the concern will always be there without measurement. So I would think we should be monitoring fisheries and including things like the whales and seals that you're talking about, if they're being consumed in particular. But I have not seen any data suggest that's of concern. But again, that's partly because I've not seen a lot of data. So I do sympathize with kind of the background, I think, of your question.
Thank you. I think this is a good place to end. We're just about out of time. Ken, is there anything else that you would like to add in closing?
Well, I just hope people can, maybe educate a little bit themselves by looking at what we're providing. I try and sum things up and really say that radioactivity can be dangerous. It is of concern. It was and still is off Japan. I'm not expecting that same level of health concern on our coastline, but to reach that conclusion, we need monitoring, we need measurements, and so far it's taken people, the public, to really make that happen in the ocean and the water, and I hope it continues for other isotopes and other fish and mammals and other things. So we need your help both to keep this going directly and to tell your representatives, your elected officials, that it's a concern and they should be starting these monitoring programs. Thank you.
Thank you. And Bob or Pam, do you have any concluding remarks?
I just want to say thank you for the opportunity. This was really informative.
Thank you.
I have one last question. That was about the Canadian data, the policy to get rid of all of their ocean or fish data. Is that going to impact anything as far as we're concerned?
Well, I'm not familiar with that specific. I know they are producing ocean data that's been released by Canadian Fisheries. Sorry, I can't answer the specifics.
Okay. Thank you. Pam, did you want to say anything else before we close? If people are interested in participating in monitoring on St. Lawrence Island?
No, just to say I think it's a great program, and I'm just very interested in helping to set up additional monitoring stations on St. Lawrence Island and elsewhere in Alaska, places that need coverage. And I just think all of us need to encourage our state and federal agencies to do their jobs too, because there's not, as Ken mentioned, there's not, I think, enough monitoring of our fish and traditional foods that are so critical to the health of Alaskans.
Thank you. And Ken, we want to thank you again for your time today. We really appreciate you doing this. I know it's not the format that you usually do, but it works very well. So thank you very much for all that you're doing.
It's my pleasure.
And we want to remind everyone that a recording of today's call will be available on our website. So share it with your friends and colleagues. And don't forget that you can always support Che Alaska Calls with your tax-deductible contribution via our secure website at akaction.org. So thank you again to everyone for calling in, and have a wonderful day. Thank you.